Hi everyone. I hope you are doing great. I'm going to go through a couple of practice problems related to Module 8. To access the practice problem, please go to Module 8. If you click on Module 8, the practice problem folders in Module 8, and there is one file I have uploaded that has the problems that we are going to go through today. So Module 8, let me open Module 8, practice problems, and then open the PDF file and have that file open because I won't be able to share that and my laptop at the same time. So you have to go through the questions through that file. The first question. The life in hours of a 75-watt light bulb is known to be normally distributed with sigma equals to 25. We take a random sample of 21 bulbs and we measure the life of the light bulb, and the average of that 21 sample is 1014 hours. We need to construct a 95% two-sided confidence interval on the mean. Okay. So read the first two lines. And as you read the first two lines, can you tell me what is the random variable of interest? What is this random variable of interest that we are trying to get a better understanding of? Just read the first two lines. You're not. Can you repeat one? You're not loud enough. I couldn't hear you.
Light bulb.
What about the light?
The life.
Their life. The life of the light bulbs. Okay, so it's important for you guys to understand that random characteristic of interest that we are looking at, the life of the light bulbs, and it's in hours. Whatever we get, it's in hours. And then what are some other things that you get from the first two lines? Give me those.
Distribution, normal distributed.
Okay, so this random variable has normal distribution. What else?
Sigma and the mean.
Sigma 25.
This random variable has a standard deviation of 25.
And a random sample has mean. The mean is 114.
Okay, so it's important for you guys to know what does that mean. So first of all, a random sample of 21, what does that mean?
And the sides.
Exactly, n, which is sample size. Okay, sample size is 21. And then a sample size of 21 has a mean life of x bar. So what is the, okay, so the notation is x bar. So what is, I know the value, but what is this?
It's the sample mean.
Sample mean. And that's 1014. Okay, the thing, and then we need to find a 95% confidence interval on the average of the life of these light bulbs. What is the notation of the average of the life of the light bulb that I'm trying to find? Not the average of the sample, the average of the life of the light bulbs in general.
Mu.
So basically what happens here is that I know the life of the light bulbs that are produced in this company or wherever. It's definitely a random variable. It changes from one light bulb to another. I'm interested to get some idea about the average of the life of these light bulbs. But I don't have that luxury, because if I want to do that, the only thing would be for me to use all the light bulbs of this brand that exist in this world and let them die at some point, and then measure their life and then look at the average. Okay, so that never is going to happen. So I won't be able to get a sense of the actual average of the life of these light bulbs. This has a name as well. Can you tell me what is, so it's, I'm going to mention, so it's population
mean.
Exactly, it's population mean. Okay, this is called population mean. If I had access to all the light bulbs of this brand that exists in this world, and I had the luxury of watching all of them die one by one, I could measure the life of every single one of them, look at the average, and report mu. But that's not possible for me. So if I want to come up with some idea about the average of the life of these light bulbs, because I want to put them in my marketing ad, the only thing I can do is to take a sample. If to take a sample of these light bulbs. And then I'm going to look at the average of the sample and then use this average as an estimation for the mu. And then everything we learn in module 7 and module 8 in terms of confidence interval, test of hypothesis, and so forth for this unknown average are basically methods to help us to be able to say something about this unknown population parameter using our sample. We get a sample, we look at our sample, then we want to make some conclusion about these unknown parameters of the population, such as average. This process is basically what we are trying to learn in module 7 and module 8. And this process of taking a sample and trying to say something about the unknown parameters of the population, which we will never be able to exactly find, this process is called statistical inference. Okay, so this is a term that you may see in a lot of statistical analysis or the statistics books and so forth. Okay, so every time we need either to construct a confidence interval or test a hypothesis, you have to take the very first important step. And that very first important step is, do I know, let me change. So the very first important question that you have to ask yourself, if you want to construct a confidence interval or do a test of hypothesis, that very first important question is that, do we know sigma? I mean, let me write it this way. So the question is that, do we know sigma? And then the answer, there are two answers. We know sigma. The other option is that we don't know sigma. Before we explain any one of these, tell me what is sigma first.
25.
No, what is the meaning of it? Just tell me what the meaning.
The standard deviation of
Population.
the sample.
Exactly. So sigma, let me write it. Oops. Here. Okay, one more time. What? I don't know the names, but someone just say standard deviation of the sample. Do you want to think one more time and tell me what sigma is?
25.
Oh, sorry.
Go ahead. Not the value. What is?
Oh, it's the population standard deviation.
It's the population standard deviation. Okay, so sigma is the population standard deviation. Again, if I had somehow information of life of all the light bulbs in the planet, I could measure the standard deviation of these random variables, because as I said, every light has a different light bulb. Every light has a different life. So this is a random variable. If I had the possibility to look at the standard deviation of all these measures, that would be the population standard deviation. So the first question that we always have to ask ourselves is that, do we know the standard deviation of population or not? So one option is that we know the standard deviation of population. The other is that we don't know the standard deviation of population. If we don't know the standard deviation of population, given the fact that I need that information to be able to do the calculations, what am I going to use instead of sigma? I don't have sigma, so what am I going to use instead of
Just
sigma?
the sample standard deviation.
Exactly, we take sample of size n, and then we look at sample standard deviation, which we show by, what is the notation for that? Sample standard deviation?
S.
S. So we use sample standard deviation if that's not given. If the population standard deviation is not given to us, we use sample standard deviation. Then, okay. Then let's look at this one. So we know sigma, so that's scenario one. If I know sigma, the formula for constructing confidence interval for this unknown, remember this is my unknown, this is what I'm looking for, average of the characteristic of interest in the population. Then the confidence interval for mu is x bar minus z of alpha over 2 sigma over square root of n. This is a two-sided confidence interval, x bar plus z of alpha over 2 sigma over square root of n. If I need a one-sided confidence interval, one-sided lower bound, it would be x bar minus z of alpha sigma over square root of n. And if I need a one-sided upper bound, it would be x bar plus z of alpha over sigma over square root of n. So this is for the scenario where sigma is known. Now, if sigma is not known, we have to use one of these formula. Then mu would be between x bar minus t of alpha over 2 n minus 1 s over square root of n, and x bar plus t s n over square root of n, and then the one-sided would be x bar minus t of alpha s over square root of n, or the upper bound will be x bar plus t of alpha s over square root of n. Okay, so as you can see, the structure of these formulas are the same. The main differences is in the sigma here and the s here. If I know sigma, I will use sigma. If I don't know sigma, I use a standard deviation of the sample. So I replace sigma with s. That's one difference. The other difference is that if I know sigma here, I use z value that I get from the z table. If I don't know sigma, here I use t values that I get from the t table. Okay, so these are the two main differences between this set of equation. So if there is any confidence interval in the exam or later in life in your projects, these are either one of this formula or this formula. You easily get all the values that you need to plug in into these equations from the problem statement or from the real world data. The only thing that you guys have to do is to just ask this question: do I know standard deviation of the population or I don't? And then based on the answer to this question, just pick the right equation and just plug in the numbers and you're good. Okay, so just that. Now, in this example, if we see line 1, it tells you that sigma is 25 hours. Okay, so sigma is given to us. So since sigma is given, then I have to pick one of the formulas in the first set. And then it says construct a 95% two-sided confidence interval. So I have to pick the very first formula. So if I pick the very first formula, as you can see, if I wanna, just let me write these things one more time. N is 21, X bar 1000. Okay. In this example, N sample size is 21 and X bar sample average is 1014 and sigma is 25. Okay, so, and I know that I have to pick the first formula for a two-sided confidence interval when I know sigma. So all I need to is to just plug in the numbers. X bar I know. And
Do we need alpha or no?
yeah, we do. Yeah, it says in A, it says construct a 95% confidence
Will
interval.
be 0.05.
Exactly. So alpha is 1 minus 0.95, 95% confidence interval. So alpha is 0.05. So here, then in the formulation, here I have to put z of 0.025 because if alpha is this, then alpha over 2 is 0.025, right?
Sorry, but what is the name of the 95%?
Confidence level.
Okay.
So alpha over 2 is 0.025. Okay, so I need to find this value and then the rest is S, which is, no, there's sigma 25 over square root of N 21 and mu 1024 plus Z 25 over square root of 21. And here again, I have to put Z of 0.025. So to be able to find Z, go ahead.
1024? Where did that number come from?
This is the average of the sample.
Oh, okay.
I think it's 1014.
Sorry, 1014. Okay, my bad then.
Yeah, sorry.
Thanks. Yeah, 1014. Okay, so the only thing I need here is Z of 0.025. And this value, I mean, you probably should write down in your cheat sheet because these are some of the Z's that are used a lot. So this is 1.96, right? Then if I put, then if I put that value instead of Z here, 1.96, and that value instead of Z here, 1.96. And
Professor.
yeah.
1.96 is always in negative side. Why are we choosing the right side, the positive side? Because when I looking for the table of Z, I have 0.025 is negative 1.96.
0.
Yeah, if you go in negative 190, it exactly is there.
Wait.
And I find that a lot. They always put the number positive instead because it's about symmetry or something.
No, I'll explain to you in a second. 0.025, yeah. So that's the, let me change the color so everyone can see. So this is close to 0.025, or that's the closest we can find in the table to 0.025, and this is corresponds to this value, minus 1.96. Okay, so basically this is this value here, minus 1.96. Okay, so the values that we get from this C table always are the whatever value that we get, minus 1.96, the probabilities that are in the body of the table always shows things less than that value. That's why you see the blue side, the shaded blue side. So the probability of 0.024 that we see here in the body of the table that's the green shaded area. Okay, so that's always the way this table works. Whenever we find a value in the table, the probabilities in the body of table of the body of this table shows probability of less than that value, and that's exactly what you see here as well. It tells you what this table is showing to you. Okay, in the formulations here. In the formulations here, the value that we need for z, it also has been mentioned in the videos, the value that we need for z is always the positive version of that number. And if it needs to be negative, the equation always puts the negative sign for you. So in the formulas that you have to use, in all these formulas that we have in these videos, z always refers to the positive version of that number that we find from the table.
All right, thank you.
Sure. Your observation was correct, but it's just that the standard of this formulation.
So, Professor, can I ask you a question real quick?
Mm-hmm.
So usually when I get the Z alpha, I usually take 1 minus alpha, and that's the value that I find. Is that the right process? So far, it's getting me the right answers, but so for 0.025, I would take 1 minus 0.025 and then look that value up, and I would get positive 1.96.
You can do that, yeah.
Yeah. Okay.
So basically the reason is that. So okay, this value has a symmetric value here as well, right?
Right. Yeah.
So basically what is happening is that, and then this shaded area, green that I put here, is the same area here as well.
Is that why in the formula on the left side it's negative, and on the right side of mu it's positive?
Yeah.
Okay.
So what you guys are doing, what you are doing is that basically you say you deduct this value, right? And then you look at this, you find the z of associated with this. And that's why you basically get this number, right? So you just get just a positive, that's why.
That makes sense, thanks.
Mm-hmm. But if you don't, just make sure you use the positive version. Okay. And then if we plug all these numbers, do all the calculations, multiplications, and so forth, this ends up to be 1003 less than or equal to mu less than or equal to 1025. Okay. So that's going to be the two-sided confidence interval. Now, let me see, do I have a hypothesis test here? No. Let's assume, this is not in the question, I'm just making this up. So let's assume I was testing a hypothesis, and this is my hypothesis, that the average of the these light bulbs that I don't know is actually 1020 hours. And my alternative was that that's not correct. You have taken a sample of size 21. You calculated your average as it was given to you here. You have the standard deviation of population, and this is the confidence interval that you have developed at the end of the day. Can you make a conclusion about this hypothesis test using this confidence interval?
But usually we compare the z. That means x minus mu 0
okay,
over.
I don't want to use that method.
Okay.
I'm just asking, can you make a conclusion about this test?
Yes.
Confidence interval. Give 30 seconds to everyone to think. So this confidence interval is a 95% confidence interval. And what does that mean? That means I'm confident. I'm 95% confident. This unknown average of the population falls somewhere in this interval. I don't know what is the exact value, but I know it's between 1003 and 1025, and I'm 95% confident about that. That's what this confidence interval is telling you. Knowing that, how would you make a conclusion about this test of hypothesis? Are you going to reject H null, which says that, oh, the average is actually 1020, or you are going to fail to reject? 10
You
seconds.
would, oh, sorry.
Go ahead.
You'd fail to reject, right?
Because?
Because the mu falls within the confidence interval.
Exactly. So here in this confidence interval, as I said, tells us 95% we are confident the unknown average falls somewhere in this interval. And then I'm telling you, I'm actually thinking the average is 1020. Okay, the 1020 that you're thinking about is in this interval that we know contains that unknown average. So if that's the case, I don't have any evidence to reject the null hypothesis. That's why we in the null hypothesis, it's important to say, we never say we accept the null hypothesis, because I don't know if this is correct or not, but I don't have any evidence to reject it. That's always the correct statement for the hypothesis test. We always say we fail to reject, which means with the confidence interval I have constructed and everything I see, I don't have any evidence to reject this thing. So I'm just going to accept it. So I don't have evidence to reject. So that's why I say fail to reject or reject, but I never say reject or accept. Okay, so this is important. Anyway, just pay attention that you guys know how to make a conclusion about the test of hypothesis using the confidence interval. Not only in the real world, but also in the exam, I may give you a hypothesis test, something like this. And then I may give you a confidence. I may tell you, oh, we took a sample. This is the average of the sample. And this is the lower bound and upper bound of a two-sided confidence interval. I give you the confidence interval, and I would ask, are you going to accept this null hypothesis or reject it? And then, are you going to reject it or fail to reject it? And then you have to make the conclusion based on just what we just talked about. Okay, so make sure you guys are comfortable with that.
Professor, I just wanted to clarify for the confidence interval. So you're saying we're 95% confident that all the data samples or the population will fall within that range, right?
No. Mu, average.
Okay.
I'm not talking about every single light bulb that I get. I'm not talking about those. I'm just talking, I'm just talking about this average of the life of these light bulbs that I don't know. And I take a sample of size n, and I look at the average of the sample, and I want to make inferences about this unknown mu. And this confidence interval that we constructed helped me with that inference, because this confidence interval means I don't know the mu, I don't know this, but I can tell you that I'm confident with 95% that this unknown mu falls somewhere in this interval. That I can tell you. And then you can go ahead and make conclusion or make some decision that maybe in your product you want to use this light bulb, and is this life okay for you, or you prefer it to be more or less or whatever. At least you can make some decisions based on this piece of information that I give you here.
Okay, thank you.
Sure. Okay. Okay. And then we need to construct a 95% lower bound as well. So the formula for the lower bound, x bar minus z of alpha, sigma over square root of n. Mu, again, we have everything, 1014. The only thing I have to find out is z of alpha. So I know sigma, which is 25 over square root of 21. And z of alpha here would be z of alpha is 0.05. Z of 0.05 and z of 0.05 is 1.65. Again, I would recommend to know z of 0.025, z of 0.05, z of, I would say even, I think these are the two that I'll have seen a lot, and you see a lot in the examples, but at the very least these two. Okay, and then this is going to be equal to mu, and then when we do the calculations, this is what we get. Okay, that's the one-sided confidence interval. Okay. Now let's go to question 2. If there's no question regarding the first one that we just did, let's go to question 2. Okay, I need your help with question 2, given the fact that we went through a test of we went through the confidence intervals and everything. So help me with question 2. The number of steps to cover the same distance was measured for 41 randomly chosen people. The same mean, the sample mean is 2220 steps, and the sample standard deviation is 444 steps. Assume the distribution to be normal. Construct a 90% two-sided confidence interval on the mean. Okay. Okay, so first tell me, what do you have from the first two lines? What are the information that is given to you? First of all, tell me the random variable. What is the random variable?
41.
What is it?
41?
No, what is the definition of the random variable of interest that you're trying to say something about?
The number of steps.
The number of steps.
Exactly. The number of steps covering a specific distance. Okay, that's my random variable. What else do you have from the first two lines?
N is 41.
N, our sample size is 41.
X bar is 2220.
Sample average, so you see it says sample mean, 2220, and
S is already given, S equal to 444.
when you are reading, so if, let's assume here I hadn't given you S, so I would just given you the sample standard deviation is 444, okay? If that was the case, you have to know, you have to read the problem carefully and see that this is sample standard deviation, not just the standard deviation of the population. So what is given to you is sample standard deviation. And what is the notation for that?
S.
S is 444. And what we need to do is to construct a 90% two-sided confidence interval. Okay, as always, what is the very first question that you have to ask yourself when you want to construct a confidence interval or answer a test of hypothesis?
Do we know sigma or not, the population standard deviation?
Exactly. Do I know sigma? Do I know sigma here?
No.
No, I don't know. If I don't know sigma, then which set of formula should I pick, the top one or the bottom one? This is when I
The
know
bottom
sigma.
one.
Yeah, the bottom one is when I don't know sigma. If I don't know sigma, then I have to pick one of these formulas. In part A, it says a two-sided 90% confidence interval. So I have to pick the first formula, but I know it's already in this set. Okay, so when you put together your cheat sheet, make sure to put these formulas separately. These are the formulas when sigma is known. These are the formulas when sigma is not known. As soon as you figure out that sigma is known or not known, just make sure you're picking the right formula from the right set. Okay, so let's go to this two-sided confidence interval. So the formula is x bar minus t cs over square root of n Okay, so that's the formula. And as you can see in this formula, I have S, it's here. I have X bar, it's here. I have N, it's here. The only thing I need to find out from the table is T of alpha over 2 and N minus 1. Alpha is 0.990, sorry, alpha is 1 confidence level is 90%, so alpha is 1 minus 0.9, that's 0.1. So alpha over 2 is 0.05, and N minus 1 is 41 minus 1 is 40. So I need to calculate to find T of alpha over 2 and N minus 1. I don't have T table in my iPad. Please go to module 8 and open the T table. So the T table is uploaded on module 8 folder. So please open that. It's important for you guys to make sure that you can find the right value for the T from the T table, because as you can see, the formula you are getting it from the cheat sheet. Everything else is given to you in the problem statement. So if you can find the T value correctly from the table, the rest is just a bunch of multiplications and divisions, and there is no reason for you guys to get the wrong answer. Okay, so open the T table, and this is what I want to find. So I want to find T of alpha over 2.05 and degree of freedom of 40, new 40. So tell me what
40, let's see.
that value.
So yeah, 40 and 005.
I see 1.684.
Yeah, 1.684.
Exactly. So make sure you guys, all of you, are comfortable with this to find the right T value and Z value from the table.
I have a quick question for you. Do we have to be very exact with interpolating between values, or can we just kind of get a rough in-between?
For the exam, I'm not going to give you any question that would need interpolation, but if you in the real world, if you are going to interpolate, just pick the 2 points and really perform the interpolation too.
Okay, thanks.
Okay. Okay. X bar. Then here I have 41 minus 1.684 S 444. And when we do the calculations, this is going to be 2103, 2337. Okay, so that's my two-sided confidence interval. That's my 90% confidence interval. Can you give me one sentence what this means?
%90 of our average is between these two numbers.
No, not exactly.
Would it be we are 90% sure that mu is in between these numbers?
Exactly. We are 90% confident that the unknown mu falls somewhere in this interval. This is how you have to basically say it or interpret it. And then, similar to the previous problem, let's assume I'm testing this hypothesis that the mu is 2100 and mu is greater than 2100. What would be your conclusion about this hypothesis?
Professor, isn't this a two-sided test? So it needs to be not equal to for the alternate hypothesis.
Yeah. Oops. So what is your conclusion? I think this unknown mu that I'm looking for is 2,100.
We fail to reject. It's 0.
We fail to reject that this is the unknown mu.
Mm-hmm.
Why?
Because mu is in the interval of the confidence.
No,
It's less than
We reject it.
2,103, so
Yeah.
we'd reject it.
We reject H naught because I'm saying that I'm 90% confident this unknown mu that I have no
over
idea
there.
about is in this interval. Now I'm telling you, I'm thinking actually mu is 2,100. And you're like, no, mu is somewhere in this interval. Mu is not 2,100. So in this
I was
scenario,
just confusing about two sides.
no worry. In this scenario, I'm going to reject the null hypothesis. Okay.
Here it wasn't asking, right? This is an extra question you're asking.
Yeah, exactly. So I'm just
Okay.
since we already extracted the confidence interval, I'm just making up this hypothesis test and say, what would you conclude? You may get similar questions in the exam. I may give you the hypothesis. I may give you the lower bound and upper bound of the confidence interval. And then I may ask you, what is your conclusion about the test? So you have to just make that conclusion. You don't need to calculate anything, but you just have to be able to do an inference about this hypothesis using this confidence interval that you have constructed. And that's it. Okay, then we want to construct a 90% lower bound and upper bound. So I'm just going to do one of them for the sake of time, but the other one is similar. So if we want to do a 90% lower bound confidence interval, that's x bar minus t of alpha n minus 1 x over square root of n. And that's 2220 minus t of alpha and minus 1. That's t, sorry, that's t of 0.1. T of 0.1, alpha is 0.1, right? And n minus 1, what was it? 40. And let's go to the t table one more time and find this value for me. T of 0.01 and 40.
2.423.
1303.
Oh, sorry.
One 0.1 and 40.
Is 1.303.
Yes. Yeah. Oops. 1.303. So then here it's 1.303 multiplied by s, which is 444 square root of 41. And then after we simplify and everything, it's going to be 2130 less than or equal to me. So we are, if we are looking at a one-sided confidence interval, we can say that we are confident. We are 90% confident that this unknown mu falls somewhere in this interval. And again, if you were doing the same test, this basically means mu greater than this, right? And if you were doing this test, and this was the confidence interval you had constructed, and I'm asking you to make this test, you make the same conclusion. You believe with 90% confidence that this unknown mu falls somewhere in this interval, but I'm asking you that mu is 2100. So obviously here you would reject
Reject.
the null hypothesis because it's not.
Professor, can I have a question?
Go ahead.
In the lecture video, it say that when the sample size larger than 30, we have to use the t-test. But here, why do you use a t-test?
Here it's because the sample standard deviation is given to you.
Oh, so if it's not given, then we have to use the z-test?
Yeah. So if you have population standard deviation, you can use the z-test. You can use the z. But if sample standard deviation is given to you, you can use t.
Is the z-test in chapter 7 or it's chapter 8?
Z is chapter 7, t is chapter 8.
Okay, thank you.
Basically, chapter 8 is the same chapter 7 when we don't know sigma. Okay. During an independent research, 2,500 landowners were interviewed. Okay, so now let's look at question 3, which was related to this last part that I made available today. During an independent research, 2,500 randomly selected people were interviewed, whether they visit their dentist for a regular dental check or not. Only 2,000 of them gave a positive answer. We want to calculate a 95% two-sided confidence interval on the population of people who regularly have a dental checkup. Okay, so construct a 95% two-sided confidence interval on the proportion of the population who regularly have a dental checkup. So here, the random characteristic of interest is, I don't call it the random variable because, so the characteristic of interest is,
So here when it's saying it's 2,000 people gave like positive answer, does it mean like 2,000 people said yes, or only like 500 people didn't want to answer?
No. They said yeah. We assume everyone answered.
Okay.
Yeah. So the characteristic of interest here is the proportion of population that visits the doctor regularly. Okay, so this is what I want to find out. And the notation for this is what? How do I show this proportion? What is the notation?
P.
P. So the proportion of population that visits the doctor regularly, that's P. I don't know this P, similar to the mu. If I want to know what percentage of the people in the US visit their doctors regularly, I have to go ask every single person if you visit your dental doctor regularly, and when they answer, I can find out the value of the P. But I won't be able to do that, right? So I won't have a way to find the proportion of people that meet their doctors regularly in the population. What I can do, similar to what we did for mu, is to go and take a sample. So here, we take a sample of size 2,500. That's the sample. I go and ask every single person, do you visit your doctor regularly or not? Some of them say yes, some of them say no. 200 of them gave a positive answer. The notation for that, so we call the positive answer success. The notation to show the number of success in this 2,500 basically experiment that we ran is X. So these are the number of success in this number of experiment or the sample size that we collected. So this is number of success. And this is my sample size or number of experiments that I ran. Experiments. And then if I calculate X divided by N, what does that give me? 2000. That's going to be 0.58. What does this number give you?
The sample proportion,
What does that mean?
the number of successes in the sample.
The proportion. So this is sample proportion. Similar.
It's 0.8.
Is it 0.8? Yeah.
Sorry, zero, is it 0? Yeah. Maybe I didn't look at the answer. Yeah, 0.8 right now. That's 0.8. So this is sample proportion. Similar to the mu, what I need is the population proportion, P. However, I have no way to calculate it. What will I do? I take a sample. I take a look at the proportion in the sample that has that characteristic of interest. And what is the notation to show the sample proportion?
S.
P hat. Okay. So that's the notation to show the sample proportion. And then if I want
It's the same like the S, right?
you repeat one more time?
It's like P with the head is the same as the S.
No, it's no S
Like
is the standard. S, give me 1 second. S measures variability around mean. That's what S measures for you. Standard deviation, or for the population is the standard deviation of the population or variance. These are measures of variability. P is just a proportion of something in the population. It has nothing to do with variability or anything. Two different measures. So P, as you can see, X divided by N. I took 2,500 sample. 2,000 of them told me they visit their doctor regularly. So that means 80% of this sample that I took visits their doctor regularly. You know that from the sample. However, you want to make some inferences about this proportion in the population. What kind of inference you can make about the proportion of people that meet their doctors regularly in the population? That's what we want to do. Statistical inference, again. I look at the proportion of the sample to say something about the proportion of the population. Similarly, we look at the average of the sample to say something about the average of a characteristic of interest in the population. I want to do the same. Look at P hat and say something about the proportion of a characteristic of interest in the population. Okay, now if I want to construct what does this say? Calculate a 95% two-sided confidence interval. The formula, you have it, is P hat. Okay, that's the formula for a two-sided confidence interval. And obviously here, I have the value of P hat. That's just we calculated here, the 0.8. The only other thing I need is Z of alpha over 2. And alpha here is 95% confidence interval is 0.05. So alpha over 2 is 0.025. So Z of 0.025 is 1.96. So I have used that number so many times, so I just know it. Then if we replace everything, that's 0.8 minus 1.96, 0.8, 0.2, 2,500. And when we do all the calculations, this is going to be 0.784. So this is a 95% confidence interval for proportion of population that meet their doctor regularly. What does that mean? So how would, okay, can you say this to me in just sentence instead of just saying the confidence interval is this? Can you say it in one sentence? You are 95% confident that
the proportion of the people are in between these two numbers.
Exactly. We are 95% confidence that the proportion of people that meet their doctor regularly falls somewhere in this interval. I don't know the exact value, but I'm 95% confident it falls somewhere here. Okay, so that's basically our conclusion. And similar to test of hypothesis part. So let's assume I'm giving you a test of hypothesis. My null hypothesis is that P, oh, we already have it here, right? Or no? No. Let's assume I give you a test of I tell you that P equals to 85. I'm sorry. An alternative is that P is not 85. So basically I want to test, or I claim that 85% of people in the US population meet their doctor regularly. What would you say about this hypothesis test?
Failed to reject.
So
One more
we
time.
reject.
No, reject.
Exactly. So I say I'm 95% confidence the proportion of people that meet their doctor regularly is somewhere between 78% to 81%. Now I'm telling you, I'm actually thinking it's 85%. Then you can say no, because I'm 95% confidence it falls somewhere in this interval. So if you're thinking that it's 0.85%, then I'm going to reject the null hypothesis because my value in the null hypothesis does not fall in my interval. Okay.
Can you say that again? I'm just getting confusing.
Sure. Okay. Do you want to tell me what this confidence interval is telling us?
Yeah, this is the proportion of population that meet their doctor, and you give us 0.85, and
Yeah.
0.85 is not exist in this.
Okay. So wait. This interval tells me exactly. This is what this interval tells me. The proportion of population that meets their doctor regularly falls somewhere in this interval, between 78% to 81% almost. I'm 95% confidence the proportion of population that meets their doctor regularly falls somewhere in this interval. Okay? So now if you tell me Okay, so I'm actually thinking that proportion of population that meets their doctor regularly is 80%. If that's what you want to check, I say, okay, actually, yeah, this is the interval that I obtained, and the 80% falls in this interval. So if you are thinking the proportion of population that meets their doctor regularly is 80%,
Fail to reject.
exactly. I don't have any evidence to reject your thoughts. So I'm going to fail to reject what you said because this is my confidence interval and whatever you are thinking about is in my confidence interval. So I have no evidence, nothing to just reject your idea. So I fail to reject your null hypothesis. However, if you tell me that I'm thinking that P is 0.85, then I would say in this scenario, I'm going to say no, because I think this interval, I think this unknown P falls somewhere here in this interval. If you think that P is 0.85, I'm going to say no, that's not possible, I think. So in this scenario, we reject the null hypothesis because whatever you are thinking about is not in the interval that we put together. So that probably is not the value of P. Is that clear?
Thank you.
Sure.
Professor, about the errors, do we have to know the errors in chapter 8 too, or?
No, I think you didn't have those in the videos. I looked at
I think that the last video that you just showed today, it mentioned a little bit about the B value, or
yeah, especially for today's video, so don't worry about those. If anything, I will give you confidence interval related to those, but I do believe you did not have much of the errors in folder 8.
Okay, so just focus on the errors on chapter 7.
Just those, yeah.
Okay, thank you.
The definition of the errors and the concept is the same if we were going to do that, because as you saw, the chapter 7 and 8 are pretty much the same. In one of them we know the standard deviation, in one of them we don't know the standard deviation. That's basically the main difference. So if we were going to calculate, still the same definition would apply. We would probably just, instead of z of whatever, we would use t of whatever we are calculating. Okay. Let's look at question 4. Let's look at question 4 to also get some examples related to tests of hypothesis. Actually, yeah, let's do question. Okay. Let's do question 4. What time is it? 8. Okay, let's question 4. We have 5-year statistics of the average amount of wheat crop harvested from a piece of land. And these are the results. Those 5 numbers, 560, 525, whatever, those are the amount of wheat that have been harvested from this piece of land. And we have been able to collect this data for 5 years. We want to test the hypothesis that the mean of the average of the wheat that we get from this piece of land is 550 versus the option that this is not correct. Okay, so first, tell me what is the random variable of interest? You have to be able to get that from the first 2 lines. What is this random? Go ahead.
The amount of wheat crop in tons.
Exactly. Amount of wheat crop in tons. That's the variable of interest. So I have a piece of land. Each year I get some wheat crop. However, obviously the value of the wheat crop each year is different from the other years because it depends on the precipitation, on the temperature, and soil quality, and so forth. I know it's variable each year. But I want to get a sense that on average, how much wheat crop I would get from this piece of land because I want to maybe do some planning. So I want to have a sense of how much I would get. So that's what I want to find, average or the average of the amount of wheat crop that I would get from a piece of land. And all I have been able to do is to look at the amount of wheat crop for 5 years. Okay, so I have been able to take a sample of size, what is your sample size here?
5.
5. I have been able to look at the wheat crop in each one of these 5 years. What are the 2 things I can get from this sample?
Alpha is equal to 0.05.
No, not alpha. So I'm talking about the sample. So what are the, so when you take a sample of the characteristic of interest in a population, what are the 2 things you can get from this sample?
Sample mean.
Yeah, the sample mean.
Average of the sample. What else?
We can take the standard deviation.
Sample standard deviation. Okay. So here, all you have is the data of these 5 samples. I haven't given you the average or the standard deviation, so you have to calculate these 2 things. So I'm just going to give it to you right now, but in a lot of real-world problems, this is the situation. You have been able to go collect some data, but you have to come and then process the data of your sample, find out what is the sample average and what is the sample standard deviation. Okay.
How we calculate the S?
Okay, let me just mention. So S, as I mentioned, S basically is an estimation for sigma, right? And sigma is a standard deviation. Sigma square is variance. These are measure of variability around mean. And why these measures are important, because I not only want to know what is the average of a characteristic of interest, but I also want to know how variable my numbers are. Are they around the average, or they can go a lot less than average or a lot more than average? If there's too much variability in a random characteristic of interest, that's not good because you can't really plan properly. But if you know there's randomness, the numbers change, but they are mostly around the average, that's a good thing. Whenever you calculate the average, you can really trust it, you can really use it, and so forth. So anyway, sigma or standard deviation is a standard deviation or variance, or measure of variability around the mean. So the way to calculate S, this is the formula. Square root of
Do we have to know this formula for the exam?
It's one of the ones that I think you had in module 6, but the formula is not hard. It is xi minus x bar divided by 2, I from 1 to n, divided by n minus 1. So here, xi basically is any one of your samples. Here you have 5 samples, so you have x1, x2, x3, x4, x5. X bar is the average of your sample, which you already have calculated, is 524. So basically when I say spread around the mean, as you can see here, what you are measuring is how each one of your numbers are far from the mean. And then you raise them to the power of 2, because all that is important for you is that how far I am from the mean. I don't care if I'm smaller than mean or larger than mean. As far as the numbers in your sample are far from the mean, that shows there is a lot of variability around the mean in your sample. So that's what this formulation measures. And then we do this calculation for all the samples you have. That's why I goes from 1 to n. In this example, I goes from 1 to 5, and then n minus 1. So this is the formula for S to measure variability around the mean. In the exam, I'm not going to ask you to do that because that needs time and all of you. So in the exam, if I tell you we took a sample I give you the average of the sample and average of the standard deviation of average of the sample and standard deviation of the sample. But it's important for you guys to know this because, as I said, in pretty much every real world situation, we don't have that. We take a sample. I have no idea what is average of the sample, what is the standard deviation of the sample. So you have to calculate that. And if you want to do that, this is the formula. Okay.
Professor,
Go ahead.
I had a question.
Go
I had
ahead.
a question regarding our grades. So in the beginning of the year, I remember you saying that you would drop the lowest.
Can you postpone your question? Is it necessary to ask it now?
It was just a question I was wondering.
You can. I'm in the middle of the question, so I prefer to finish this and then maybe you can ask your question.
Yeah, I could ask you afterwards. That's no problem.
Okay. That's okay. Now, what do I want to calculate? And then when you look at part A, it says we want to test the hypothesis that the mean wheat crop is 550. So our null hypothesis is that the average of the wheat crop is 550 tons. And our alternative is that this is not the case. And our significance level is 0.05. Okay? So that's what we want to test in part A. So how are we going to do this? I have a sample. Okay, what is the first question that you have to ask yourself when you want to do a confidence interval or test a hypothesis?
Are we given sigma?
Okay. Do we have sigma? If the answer is yes, which means sigma is known, or sigma is not known. If sigma is not known, then you have to take a sample of size n and look at the standard deviation s of sample. So sample standard deviation. Okay, that's what we are going. Similar to the rule for confidence interval. Okay, if sigma is known, we are going to take a sample of size n, we are going to calculate average of the sample, and then I'm going to put my test statistics together. Can you tell me what is the formula for test statistics? We had that in chapter 7. Okay. If sigma is not known, I'm going to put my test statistics together as well. What is the test statistic here? Sigma is not known, so I'm going to use the sample standard deviation. I'm going to take a sample of size n. I look at the average of the sample. What is the test statistics here? And what is the notation for this one? T, right? So this is my test statistics if sigma is not known. This is my test statistic if sigma is known.
Sorry, can you repeat why we're taking the T0 here? Like why we need the T0?
I'm going to do this test, to perform the test. So then to perform a test, we have to find the test statistics first and then compare that with critical value, right? So there are different ways to do a test. If you have the confidence interval, you can do it using the confidence interval. If you don't have the confidence interval, you can use the classic method. We are going to develop the test statistics Z or T, depending on if I know the sigma or if I don't know the sigma, and then convert that with critical values. So let's say we are looking at the two-sided hypothesis test. Okay. Then in the left scenario, in this scenario on the left, I want to compare my test statistics with Z of alpha over 2 or Z of minus Z of alpha over 2. If your test statistics, the one that we calculate here, falls in this range, is greater than Z of alpha over 2 or minus Z of alpha over 2, what is your conclusion?
So if the test statistic falls within the range, then you'll have to fail to reject. Wait, reject.
Exactly. The shaded area is the rejection area. This area is the fail to reject area. So if the value of my test statistics falls somewhere here or somewhere here, if Z naught is greater than Z of alpha over 2 or is less than minus Z of alpha over 2, I'm in the rejection area. Then I would reject null hypothesis.
Another name for the rejection area is the critical area.
Yeah, exactly.
And then the fail to reject area is the confidence interval.
Exactly.
Okay.
And then if it's one-sided test, then I need to compare Z of null. If Z of null is greater than Z of alpha, I would reject, or if Z of null is less than minus Z of alpha, I would reject as well. This is what we had in Module 7. Now, similar concept exists for Module 8. If sigma is not known, no worries. I'm using S, standard deviation of the sample. This is my test statistics. And here for a two-sided test, I'm going to use T null, or to compare T null with T of alpha over 2 and minus 1 and minus T of alpha over 2 and minus 1. The idea is exactly the same. So T distribution is also a symmetric distribution. So here is my T of alpha over 2. Here is minus T of alpha over 2. So if the value of the test statistics that we calculated here is somewhere in the green, is somewhere in the, is somewhere here, greater than T of alpha over 2 or less than T of alpha over 2, I reject. If it's not, I fail to reject. So if these conditions hold, we reject null hypothesis. And for the one-sided tests, it's the same. So if the value of the test statistics is greater than T of alpha, or the value of test statistics is less than T of alpha, then when we make conclusions based on that. So now let's go back to the question. We want to test the hypothesis that mu is 550 or mu is not 550.
For the one-sided T test, is for the less than, is it negative T of alpha?
Yeah.
Okay.
Thank you.
Mhm.
Okay, so this is the test that we want to run. And let me write it here one more time. Now, mu is 550, H1, mu is not 550. And we took a sample of size 5. I know the X bar. I know sigma. And test the hypothesis, and I know the alpha. Okay, the very first question we have to ask yourself. We have to ask ourselves. Sorry. This is S, not sigma. This is S. Make sure to correct this, guys. The very first question we have to ask ourselves. Do we know sigma? Has the question or problem statement has given you the standard deviation of the population? In this case, no. I have a standard deviation of the sample. If the answer is no, I have to pick the formula on the right side. That's where sigma is not known. I have to pick the formula on the right side. Then T is X bar minus U, not basically divided by S over square root of n. And here when I said mu, basically I mean mu naught, because in the hypothesis test, remember this is what we call, whatever we put here, we call it as mu naught. We say mu equals to some mu, we call it mu naught. So here what I put here is basically that number. Okay. Okay, now X bar is 524. Mu naught is 550. S is 27.68. Square root of n. Square root of 5. Look at the results. So that's going to be minus 2.05. Okay? And this is a two-sided test. So the critical values that I need to find are T of alpha over 2 n minus 1 and minus T of alpha over 2 and n minus 1. Alpha here is 0.05. So alpha over 2 is 0.025. So I have to find T of 0.025. N minus 1 is 5 minus 1, which is 4. So let's find this value from the T table. 0.025. What is your value? What number did you find?
2.776.
2.776. So, and then the minus T alpha obviously is going to be minus 2.776. So when I calculate, so remember when I calculate my test statistics, this is T of alpha over 2, and this is minus T of alpha over 2. And I found the value of my test statistics, and it falls either here in this region, critical region, or this critical region. Right now, the T of alpha over 2 that I have obtained is 2.776 or minus 2.776. And the value of test statistics T0 is this value. Tell me your conclusion. How do you compare the value of the test statistics with these critical values?
Fail to reject because it's in between.
Exactly. So the test statistics falls somewhere here, minus 2.05. So we fail to reject. Okay. In the fail to rejection. So here, because the test statistics is not in the critical region, which is the red area, the red shaded area, we fail to reject null hypothesis. And then it says define a 95% confidence interval on the mean. We already did a bunch of confidence interval examples, so I'm not going to put too much time for this. So but I'm just going to give you the value and the formulation. So the formulation, we know, right? We just talked about it. I'm just going to write it really quick. Right, we did 3 examples of confidence intervals, so that's why I prefer to pass this part quickly and try to do a couple of other examples. But I just want to mention, so when we plug in the value of the x bar s and the square root of n, do that on your own for sure as a practice. This is what we get for confidence interval. Okay, so this is my 95% confidence interval. And still we wanna do the same test. This is my test. Still I wanna do the same test, and this is my confidence interval. Can you tell me your conclusion? Assume we didn't do the test statistics problem. You just have the confidence interval, you have your test. What is your conclusion and why? Guys, you know this, right?
Fail to reject for the same reason.
Okay, so 550, I'm thinking mean is 550. And this confidence interval that I developed, that I believe contains the unknown mu, is from 490 to 558. And if I'm thinking that mu is 550, if that's my null hypothesis, this actually falls in this interval. So yeah, so I don't have enough evidence to really reject this null hypothesis. I just fail to reject it. Okay. Okay.
Could I ask a question about the sigma? In a real situation, when would you actually know the population mean?
Population mean or standard deviation?
Oh, sorry. Yeah, the population standard deviation. When would you actually know sigma? Would that be like there's a lot of previous experiments that have been done and you're running off of that? Because any situation I run in my head, you could get S, but not sigma. You wouldn't know that.
I can also think of many, unless you have similar other, yeah, you maybe have some extensive data about some characteristic of interest that helps you to get a sense. You may have data of some other characteristic of interest that are random and are similar to the one that you are thinking about, and they may have sigma, and you may be able to use some of that estimation. But I myself, in my research is in public health, so I use huge surveys of health of the population, their weight, their height, their blood pressure and things. In my research, I basically try to predict how the health condition evolves over time and what are the healthcare costs and what are some of the interventions that help and so forth. So I work with these big surveys of data of healthcare of people, and none of those, and in none of those basically projects we assume we know the standard deviation of that characteristic of interest in the population. we always use that sample. Although they are huge samples, for example, we use healthcare surveys, which are hundreds of thousands of people in these surveys in the US, but still we use the sample standard deviation and not the population.
I see. And if you were using the population standard deviation, it seems like there'd be an ambiguity in the way that, like, if you reject the null hypothesis, you say you use a sigma value when doing that. And so how do you know that you're actually rejecting, that it's not sigma that was off instead of the population mean?
So one of the things that we did in chapter 7, when we calculated alpha and beta, I think in some of the examples that you had, we showed that these are all the errors. Exactly when we talk about type 1 error or type 2 error in a test of hypothesis, that's exactly what those errors are. Type 1 error says, what if I reject H null while H null is correct? That's type 1 error. Type 2 error says, what if I fail to reject H null while H null is wrong actually? Those are exactly the errors that you are talking about. So in the test of hypothesis, when we design a test, all we want to do is to somehow design a test such that the chance of these errors is as low as possible. And one of the things that we can play with to reduce the chances of this error is sample size. And that's why in a lot of, especially again in public health, when we make some conclusion, they always question the sample. Do you have enough sample to trust your conclusion? But obviously sample size is something that we always play with, or basically the only thing we can play with. So because basically our idea is that as the size of sample increases, your sample gets closer to your population, right? So whatever you get from your sample then can be applied really to your population with a higher chance. So that's why sample size is the critical thing in statistical analysis. And that's why always, when we submit a paper or anything, always they question our sample size and they question if it's large enough to be able to trust anything. And that's what we are trying to play with in all these statistical inferences to make sure our type 1 and type 2 errors are small enough so that we can trust our inferences. Okay.
That makes a lot of sense. Thanks.
Sure. Okay, 8:38. Let's see. Question 5 is just another test. There is nothing tricky about it. You read the question, make that important decision. Do you know sigma or not? If you know or not, pick the right formulation from the right or left side. Do we just develop? Run the test. There's nothing tricky about it. Question 2. Oh, sorry. Why do you have the question? Question 6. I mean, it's the first question in page 2. So that's question 6. The oxygen concentration is exactly similar. The only thing again in that question is that I have given you all the data of the sample. Instead of just telling you, I took a sample of size 20 and this is the average and the standard deviation of the sample, I have given you all the information of the sample. So you have to calculate the average and standard deviation. And just so you don't, I'm not going to go over it right now because it's not really a hard question, similar to the numbers we have so far, similar to the examples we have had so far. But if you guys want, write down these values. The average of the samples in question 6, which is the first question in page 2, I'm giving you the average of the sample and the standard deviation of the sample so you guys can do it as an example on your own.
You're not going to give exactly like this question in the final, right?
Yeah, so I give you the average. So that's why I want to give you the average of the sample and the standard deviation of the sample so you can do the rest of the question just as a practice. But, so the average of these 20 samples that you see in question 6, the first question of page 2, the average is 3.2 and the standard deviation is 2.12. Again, there is nothing tricky about this question. Find out if sigma is given to you or not, pick the right formulation and plug in the numbers. And and construct a confidence interval and also make the conclusion about the test of hypothesis based on the confidence interval. Okay, let me just do the last question that's related to the proportion, so that helps.
So for question number 2, part B, the alpha is 0.05 and part C is the same, right?
Yeah. It's
Okay.
Once a 95% confidence.
But it's different way of saying it.
Yeah, exactly.
Okay.
Okay, so let's just quickly do last question, which is basically question 7. So that's basically the last question of page 2. I just forgot to change the numbers. So yeah, that's the last question of page 2. So here, I want to do a hypothesis test. H null is P equals to 0.6. H alternative is P is less than 0.6. And here you have a bunch of information. N is given you as 494. Can you tell me what is this?
Sample size?
Exactly. This is your sample size. I'm looking at the proportion. X has been given to you as 287. Can you tell me what is this?
Sample mean?
The success, sample success.
Number of success. Two things. If it was sample mean, it was X bar. That's one. Second thing, we are looking at the proportion. When we are looking at the proportion, we don't look at sample mean. We are looking at the size of the sample and number of samples that have turned out to be success. We asked them a question: are you going to watch NBA for the next season or not? Which is going to start in December, and I'm excited for it. So the answer is yes or no. So that's basically, so let's say this P is the proportion of the population that is going to watch NBA in the new season. That's 60% of the population. So when I get a sample of size 494, I'm going to ask each one of them, are you going to watch NBA or not? If they say yes, I'm going to count them here. So 287 is number of those people, number of those 494 people who said yes. I define yes as success in this question or whatever test it is. So X then is number of success in these 494 experiments. Then what can I get from these two?
The P
hat
equal X over N.
Exactly, P hat, which is 287, 494, and this is going to
the sample portion.
Sample proportion, and the value is going to be.
See, 287 divided is 0.6.
Yeah, 0.58.
58. Yeah.
Exactly. So this is what we call as sample proportion. Okay. Then what else do we want?
Do we know?
Go ahead.
Do we know like the standard deviation, something like that? Standard deviation?
No, for the proportion, we don't deal with any one of those.
Oh, okay. I thought it was like similar.
Yeah, if I'm looking at P, I don't deal with any one of those. All I want is a sample of size N, and all I want is number of success in this sample of size N, and that's it. X bar and C and things, none of them are here. X bar and S and all of that, none of them are here. So here, then, if I want to construct a 95% upper bound, oops.
It would be P hat plus Z over L2, no L2.
Let's look at the formula. So the formula for the upper bound confidence interval is P less than equal to P hat plus Z of alpha alpha here is. Did I give you the? Oh, no, it says, yeah, it says already 95% upper bound. So that
Yep.
alpha is 1 minus 0.95, which is 0.05. So it automatically gives. So if I tell you construct a 95% upper bound confidence interval, lower bound, or two-sided, that's all you need. You shouldn't ask what is alpha. I gave you the confidence level 95%. So find the significance level automatically. So anyway,
Always same 164.
yeah, 1.64. And that's going to be less than or equal to 0.61. Okay.
Sorry, there was a formulas like PV is equal to 2P of Tn minus 1 greater than T0 for two-sided, or if it's one-sided, it's PV is equal to P Tn minus 1 greater than T0.
It was
It's P values, and the T dot is X bar minus mu over S over square root of N.
okay, give me 1 second. Let me do this test. Let me finish this, then if you don't find the answer to your question, then we can look at it. Okay.
Thank you.
Sure. Okay, here I found the upper bound confidence interval. So basically here it says I'm 95% confidence. The proportion of population that has that characteristic of interest is in this interval, is less than 0.61%. So if that's the case, if this is the confidence interval that you have, and this is the hypothesis that you are testing, what is your conclusion then?
We reject.
I'm 95% confidence that the proportion of interest in the population is less than 0.61. And
Fail to reject.
And here I'm thinking, oh, actually I think it's 0.6. So 0.6 is in this interval.
Yeah, is this in there?
Okay, so we fail to reject. Make sure to pay attention, and for the exam, you don't want to make those mistakes, okay? Because you know the concept. You just want to make sure you pay attention and don't make the mistake. Okay. Okay, we decided about the test using the confidence interval method, which we already did a couple of times. Let's also decide about the test using the test statistics method. And for a proportion of the population, when we want to test P, the test statistics is this. And it has a Z distribution. So it's X minus N P. And this P null that I put in this formula is basically this one. So this number here is what I call as P null. Okay, so this is P. So then here X is 287. Those are the number of success. Minus 494.58. Oh, sorry, not 58. The P null is this, right? Is this here. That's P null. That's 0.6. And 0.6, and then 1 minus 0.6, which is 0.4. And when we do all that calculation,
Because we say hey, just one time, a week. They have another class.
are you talking to us? Okay, so that's Zeno. And then this is a one-sided test. I want to compare Zeno with minus Z of alpha. And this is a 95% test, so I need to find minus Z of 0.05. And here this number is minus 1.65. Okay, so this is the critical value. Minus Z of alpha is minus 1.65. And the value of the test statistics here is minus, the Z here is minus 0.863. What is the relation between the test statistics and the critical value? So this is the critical value.
Fail to reject because it's not in the critical value.
Exactly. So we say we reject if this condition holds. However, the test statistics that we obtain is not less than critical value, is greater than critical value actually. So we fail to reject. And that's the exact thing that we also concluded with just confidence interval. Okay, can you calculate the p-value for me? How do we calculate p-value? You have the value of your test statistics. How do you calculate p-value?
Two times the test.
This is a one-sided test. One side. So p-value is basically the probability of your z to be less than your test statistics. Probability of z less than minus 0.863. Okay, so this is a one-sided test, right? We are looking at, so this is our test. H0 is p equals to 6.6 and H1 is p is less than 0.6. So we found the z of alpha here, minus z of alpha, and we said if the test statistics is less than z of alpha, right? So this is z of alpha. If the test statistics is less than z of alpha, which means the test statistics falls somewhere here, then we reject null hypothesis. When we did our calculations, we realized that z of alpha is minus z of alpha is minus 1.65. We realized that the z minus z was 1.65, and then the value of our test statistics also ended up to be minus 0.86. So since the value, and this is our z naught, since the value of our test statistics is not less than our critical value, then we failed to reject H0. Okay? Now, if I want to calculate p-value is basically this part. It's this green area. So p-value tries to calculate probability that your random variable is less than your test statistics in this one-sided test. The p-value tries to calculate the probability that your random variable is less than your z is less than your test statistics. That's this green area. So based on what you see here, the green area is my p-value. That's what basically p-value is. Probability of z less than z naught. That's p-value. So the green area is p-value. The red area is my alpha, right? This is z of alpha. So the red area is my alpha or significance level. Can you tell me, based on what you see, what should be the relation between p-value and alpha so we fail to reject?
Filter is when the p is bigger than alpha.
Exactly. You can see here, the green, the p-value is the green. The alpha is the red area. When the green is greater than red, which means when the p-value is greater than alpha, then, as you can see here, that shows the test statistics has fallen somewhere in the blue part, which is the fail to reject area. So when the p-value, the green area, the shaded area, is greater than the red shaded area, which is our alpha, we fail to reject H null. And this is always the case, no matter what type of test you are running. Is it one-sided, two-sided, one-sided upper bound, one-sided lower bound? This rule always holds. When p-value is greater than alpha, we fail to reject. For the problems that we didn't have the chance to go through, I would strongly recommend to do them on your own. They're very similar to the examples that we did right now. No tricky part, nothing. Just make sure to do them. For the confidence interval or test of hypothesis, if it's related to the mean or average of the population, always ask that critical question from yourself at the start. Do I know sigma or not? If you know or if you don't know, then the formulations are different. So make sure to pick the right formula, to plug in the numbers, and to answer the questions. And if it's proportion, like the videos of the part 3, then the test statistics and everything else is different. So since you guys look at the proportion just today, given the examples that we went through today, I would recommend please watch the proportion part again. That hopefully the examples we did today will help you to get a better sense of the proportion.
Professor, this last part was mostly of chapter 7.
Last part, you mean the P?
Like the Z here.
No, this is P, which is the proportion which you have in part 3 of module 8, which I made available today.
Yes, the new one.
Yeah, did you have the chance to take a look at it?
I did, but yeah.
Watch it one more time. In chapter 8, in module 8, part 3 is hypothesis test about the proportion of characteristics of interest in the population. So these examples that we did, the last 2 questions are basically related to part 3 of module 8. So given these examples, I would strongly recommend go back to those 2 videos, watch them one more time. I'm sure you will get a better understanding and then do the examples.